one today. Oh, fantastic. And let me see if I have more pens. Nice. This means I can actually use the whiteboard which is much nicer to write on. All right. Morning. So we're going to continue with our discussion on recurrent neural networks. I'll wait for a couple of minutes until Danish gets my clicker. But then, do you have any questions about everything that we have covered so far? Anyone? There aren't enough people over here to even ask questions. It's amazing. Okay. Thank you. So the horrible thing is that my TAs are absent, so there's nobody actually monitoring Piazza. Can someone monitor Piazza for me? Yeah? If there are any questions, just let me know. Okay. So we're going to be continuing our discussion on recurrent neural networks, and we're going to sort of pick up where we left off. The last topic we discussed was the problem with defining divergence functions for recurrent networks. Because sequences go in, sequences come out, how actually do you relate the sequence that goes in with the sequence that comes out? And how do you relate the target sequence that you might want to the sequence that actually comes out of the network? Now, both of these are issues. So here's the whole business of consuming sequences and generating sequences from the consumed sequence is what we'll call sequence-to-sequence modeling. So the general idea is this. You have some sequence, x1 through xn, so you have n symbols going in, n inputs going in, and you have a sequence of m outputs come out. Now, I'm warning you that today's lecture, and if this leaks into the next lecture, the next one, are going to be slightly symbol heavy, so bear with me, right? So tasks like these, typical tasks, speech goes in, speech recognition, speech goes in, a sequence of words comes out. Or machine translation, a word sequence goes in English, an English word sequence goes in, a French word sequence comes out. Again, this is a sequence-to-sequence translation task. Or a dialogue system. The user's response goes in, the system's response comes out. That too is a sequence-to-sequence modeling task. Also can be performed using a recurrent neural network. Or a question answering system. A question goes in, an answer comes out. That is also a recurrent neural network. So as you can see, recurrent networks can address a great number of different problems. They are very versatile. And the key point over here is that the length of the sequence that goes in may bear no relation to the length of the sequence that comes out. So for example, speech recognition. Speech goes in, out pops the text, which tells you what sequence of words was actually spoken. So you say, this is the waveform for I ate an apple, and the sequence-to-sequence system, which is your recurrent neural network, is supposed to consume the sequence of features derived from the input speech and produce I ate an apple outside on the other side. Or if you were performing a machine translation task, you type in I ate an apple in English, and it's supposed to process it and produce Ich habe einen Apfel gegessen. So this is in German, right? I've switched it from English to German. Now, there's something very different between these two tasks. Can anybody tell me what the difference is? Anyone? Nan? Yes?
For speech, usually the order is the same, because like when I say I, it's the same position as the sentence.
Right. So here you have this issue, right? The order in which stuff goes in is the same as the order in which stuff comes out for speech. Whereas when I'm performing machine translation, what went in was I ate an apple. What came out is ich habe einen Apfel gegessen. Now the ich is the I, the first symbol became the first symbol. The second is ate. That came out all the way at the end. The last one here is apple. That ends up becoming the second to last symbol. So the order also gets changed. Not only is the number of symbols different, the order in which they appear is also different. Whereas in the first case, although the length of this input and the length of the output may not be the same, they're kind of order synchronous. So they're two different kinds of problems. Today we're going to be focusing on the first kind of problem, where the output is order synchronous with the input, but the length of the output has no bearing or has no direct bearing on the length of the input, right? So let me correct that. The length of the output depends on the length of the input, but does not have to be exactly the same as the length of the input. So consider this. You have something, the situation is going to be something like this. You have an input and you have an output. The input and output sequences occur in the same order, like in speech recognition. You have a sequence of speech frames going in, and at various points of time, the network is going to say, I heard an ah, I heard a b, I heard a d. It's going to pop answers out, right? So that is a generalization of this problem over here. Consider this. We saw various kinds of networks that were possible a couple of lectures ago. So over here, look at the structure. You have a sequence going in, and then once the entire sequence goes in, a single answer comes out. This is the basic problem that we are addressing. So if I'm performing speech recognition, I'm trying to recognize a phoneme. The entire segment of speech corresponding to a phoneme will go in. When everything is heard, it's going to say, I heard an ah. Now, the general speech recognition problem is a generalization of this basic structure, except the structure looks like this. You have inputs going in. If you look at each one, this portion looks just like this. Once this output has come out, the next portion also just looks just like this, except it's getting some additional input from what was processed previously. So the larger network is basically a generalization, but a very non-intuitive, non-simple generalization or extension of this basic network. So yeah.
Sorry to interrupt. The menu Q1 here hints that the voice representation of the language is longer than the words version. Right?
Yes. So over here we're going to assume that the number of output symbols is fewer than the number of input symbols. I was going to get to that, but thanks for mentioning it. Yes, because the way if you look at it, the number of locations at which you're producing an output is different from the number of locations in which you're producing an input. Now, if you want the output to be longer than the input, even the notion of time kind of goes away, or you would have to assume that the output continues after the input has ended, which will bring us to the next lecture. Okay? So let's consider the basic model. The basic model is something like this. You have a sequence of inputs going in, and once the entire sequence is consumed, a single symbol is output. This is very trivial. We have no confusion about how the processing here might be performed. But then here you do have to worry about how do I train such a system. So here you would have examples, little sequences over here, and the corresponding output. I'm using speech as my example, but again, keep in mind that there's nothing specific to speech. Any kind of process where this kind of output is required would still have the same kind of data. We'll see another example in a few seconds. So here, if this were speech, I have a sequence of speech frames corresponding to this phoneme. When the last frame has been read, it outputs a symbol. And then when it outputs a symbol, if you're training the system, you can compare the output symbol to what was supposed to be output. And you would compute a divergence between the target symbol here. If let's say this was a recording of the sound ah, the target output would be ah. There would be some output y at time 2. You would compute a divergence between the two. You could compute derivatives of this divergence. These derivatives would flow backwards and update all of these parameters. Again, keep in mind this is a recurrent network. So each column here is identical to every other column. The only distinction is that there's an output at the final time, right? So this makes things kind of weird. Why should there be an output at only the final time? After all, every column is identical to every other column at the way we defined it. So in other words, you really would be having an output at other times, but you're ignoring those outputs. So one simple way to actually use this kind of labeling is to extend it and say that the system is actually producing an output at every time, and that all of these outputs, if this is the actual desired behavior, then it's reasonable to assume that all of these outputs should also be the same phoneme. And so you would expect to be outputting R several times. And so now when you compute a divergence, you can compute a divergence at each point because the desired output at each time is R. You have several outputs. So you can compute the divergences at the individual times. And you computed a weighted sum of the divergences across time. And that would give you your overall divergence that you would try to minimize when you train the network. Now, why this weight over here? So, and will this apply everywhere? Can you give me an example where an assumption of this kind would actually fail, which is not speech recognition? Anyone?
If somebody is playing a game and it needs to output whether suppose some action has to be taken.
Only after the last move has been done do you know what is going on. Here, I have an example here. Suppose you're doing a question answering, building a question answering system. The question is color of sky. When you see the word color, the answer is not going to be blue. When you see color of, the answer is not going to be blue. You have to see the sky before you decide that it is blue. So here, simply saying that the output must be blue at all three times would be a patently wrong thing to be doing. But even so, I can still assume that this is the structure. The only difference over here is that the weight at these two time instants is 0, and the weight at the final instant is 1. So this weighted sum assumption is a generic assumption where you can just manipulate it by using the weights properly. Yeah.
And also, I think in this case, when you see color, there is a higher chance of blue than other words.
You can modify the weights to account for that. You certainly can, right? You can say this now has to be from this set as opposed to, potato, right? Or something else. So I'm going to focus on the class of problems where uniform weights are reasonable. Speech recognition. You can modify everything that's being said over here to other classes of problems, but for now I'm going to assume that this is the class of problems, and we will see in the next class how you can actually extend this, right? So here is the more complex problem now. We've seen for the simple problem how you would actually produce the output. We've also seen how you would train the system if you're supposed to see the entire input and then get a single output. But then let's see the more complex problem where I have an entire sequence of inputs, and I must produce a sequence of outputs, right? Now here the problem is the input is coming in continuously. At which point do I produce the symbol B? At which point do I produce the symbol E? This is not clear. The simple extension of the model into continuous output complicates matters because I have not indicated the boundaries at which the symbols must be output. So you are no longer sure exactly which outputs must be considered, because remember, every column is identical to every other column. So in reality, the network is producing an output at every time. And you need some way of deciding which of these outputs are the real ones, and which of them are just intermediate outputs that are also being produced by the network. So to understand this, let's go back and look at what the network actually produces. Now, if you have a recurrent network, and if this is really some kind of a classification task, so the output layer is typically a softmax, which means that it's actually producing a probability for every symbol at each time. So if this were a speech recognizer recognizing phonemes, these might be all the phonemes that could potentially be produced. So each of those is corresponding to each of those, there will be an output. And each of those outputs basically is giving you the probability of that symbol. But what is the probability? What probability is it actually giving you? It's giving you the probability of this symbol given all the inputs until that time. It's a recurrent network. So because it's a recurrent network, at each time, the actual output that it's producing is the probability of the current symbol given everything that has been seen in the past.
So this makes sense when you have a finite number of classes. When we were outputting blue in the previous network, how is that a classification problem? Given all the words, do we have
You would actually convert those things to classification problems. It's not you will not be working over unbounded sets, right? So at each time, you're basically going to be producing a probability distribution of all possible words, and you're going to be picking. I mean, you have to pick one of these. If you're performing generic classification, you'll probably be picking just the most likely. But here, you have to produce a sequence, right? So, and what you really want is an output of this kind, where you have outputs at specific instance of time. So the overall objective here is to find the most likely symbol sequence, S0 through Sk minus 1, given x0 through xn minus 1. So you have n inputs. You want to produce k outputs where the number k itself has not been specified, leave alone where these things must be output, right? Here's a very simple technique that I can use. At each time, I can just pick the most likely symbol. If I just pick the most likely symbol at each time, I'd get something like G, G, F, 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 I, E, E, D. And then you can group them together. And if you group them together, you say the real output is at the final, at the end of each subsequence. And so here you'd have 3 outputs. But of course, the moment you see this figure, you're going to tell me there's something wrong over here. And what would that be?
It could be that in the intermediate state, something else was more probable, but at the end of the 4 sequences, so for example...
No, I'm just picking something. I'm picking the best 4, and I'm grouping them into 1. So just if you simplify that. Something even simpler. How do I know that it was not this? Right. So when I patch everything together and saying it's only one symbol, I'm basically eliminating the possibility of repetition. And so you cannot distinguish between an extended symbol and repetitions of a symbol. Problem 1. And problem 2, the output may be meaningless. What does this feed really mean, right? If I'm trying to perform speech recognition. So then the obvious way to go over this is say, I'm going to impose external constraints. I could say, for example, only allow sequences corresponding to dictionary words. So in this case, what I have is I have this entire table of probabilities, and I would be looking for sequences in this table of probabilities which represent dictionary words. I'd pick the most likely, and I could keep patching things on. That ends up becoming a search problem, right, over this. And we'll get back to that later, right? Questions? So for now, I'm going to assume that we understand how this happens. And I'm going to refer to the process of obtaining an output from the network as the process of decoding, right? So this is, in fact, a suboptimal decode. It finds the most likely synchronous output sequence. What do I mean by the synchronous output sequence? It's kind of producing a symbol at each time, and it's computing finding the sequence, finding the most likely symbol sequence, but the most likely synchronous symbol sequence, which means that I'm producing a single symbol at each time, and then I'm patching them together. That may, in fact, not be the most likely sequence if all I'm concerned with is the symbol at the end of the line. And we will see why this is towards the end of the class, if I can get to it, or in the next class, right? So far, so good. We've addressed the issue of how I'm actually going to produce outputs. I'm going to dismiss this for a few minutes. The much bigger problem, how do I train this network, right? So if in the ideal case, I'm going to be given data of this kind. I have the input, and I'm going to tell you exactly at what time I want each of the symbols to be output. So you need to go get yourself a coffee. So if I'm telling you exactly at what time each of the symbols is going to be output, right? So in this case, how would I train it? This is, yeah?
Just the same.
This is fundamentally no different from what we did in the beginning, right? When I gave you individual segments and their outputs, I could first not switch off my screen. This is what I would have. I would have a divergence at each of these locations. Those, I can compute the divergences. I can transmit the derivatives of the divergence back through the network and update all my parameters. Or I can do this, which extracts more juice out of the symbols that are given by assuming that that symbol must occur at every time instant, right? Because we are assuming, I started with the assumption that I can assume that I can just look at a uniformly weighted sum of divergences. And then I could just compute the derivative of this cumulative divergence and feed that backwards when I'm training. So this is easy, correct? But what, and now, first, what exactly is this divergence going to look like? This is going to matter for a bit. So observe that at each time, I'm going to have a single, at any time, at time t, can you see this? dt is going to be some symbol, let me call that, what is the symbol I'm using over there? Let's say, whatever, right? I'll just call this symbol, right, for now. Then the cross entropy is going to be summation over all symbols, the desired value for the symbol times the log of the probability of the symbol. That's output by the network given the x. And this probability of the symbol given the x is simply the output of the network, which is the log of y t of symbol, right? But then this desired value is, the way we represent it, is a one-hot vector, right? All of the values are going to be 0 except for the target symbol, and for that target symbol, that d value is going to be 1. So d is going to have d has the structure. It's all zeros and a single 1 and many zeros. So that means I can actually, this summation reduces to just one term. And you're looking.
It's a little bit hard to read the.
Okay, so I'll try using a different pen, right? And also the symbols and notation I'm using is kind of bad. But if I write the cross entropy, can you see this? This is, I'm going to be summing over all of the possible symbols, the desired output value for that symbol times the log of the probability assigned to that network to that symbol at time t. This is the divergence at time t, right? Cross entropy at time t. This is just the standard definition for the cross entropy. The desired value times the log of the output, correct? But the desired value is going to have this structure. It's going to be 0 for all the symbols that you do not want and 1 for the one symbol that you want. We're using one-hot representations to represent the desired symbol, correct? And so this term, this thing, is the summation will go away. So we actually had a minus. Minus. Yeah, minus, right? So this is simply going to be minus log of y of t target symbol, which I've just written as. So what this means is that we actually produce y values. You're going to have many y values, and this y value corresponds to the target symbol. We're going to just take the log of this one y value, and that log is what we want to really maximize, right? Or the minus of that. And the rest of these can be ignored. But we're not really ignoring it because this is a softmax. If you increase this guy, the rest of them are going to go down, right? So what this means is that this divergence is simply a summation over time of the negative of the summation over time of the log of the probability assigned to the target symbol at time t, which is the output of the network corresponding to the target symbol at time t. We're going to keep using this formula, so it's useful to keep this in mind, right? So what really happens is, let's say I have my output at each time. I have an output over all possible symbols. I'm going to have many outputs, one at each time, correct? And these I have and this might be the output corresponding to the target symbol at time 1. This might be the output corresponding to the target symbol at time 2. This might be the output corresponding to the target symbol at time 3. And this might be the output corresponding to the target symbol at time 4. So all we would do is take the negative, which would be this is time. So we'd be summing across time log of y of t of the target. I don't even need to write target. I'll just write symbol t, right? The way I'm using horrible notation, but you get the idea, right? And now, when I take the divergence of this, the derivative of this divergence with respect to any given yt, what happens? At any time, that divergence depends only on one term. It does not depend on the other terms, right? So correspondingly, the derivative of the divergence is going to have zeros everywhere except for the one location corresponding to the target symbol. And at that one location, it's just -1 over the probability assigned to that symbol. Very straightforward, nothing really complicated. You've already done this several times in your recitations, in your homeworks. We're just going over this because this matters, okay? So now, let's complicate the problem just a little bit more. Instead of giving you a training data where I actually tell you exactly where each output is required, I just give you the sequence of outputs. So the earlier situation was where we had the training data, and we said, at this time, I want the output to be R. At this time, I want the output to be B. Now, I'm not giving you that information. All I'm saying is that here is the input sequence. Here is the sequence of outputs that I want produced. I'm not telling you exactly where each of those symbols must be produced. Now, this makes things a lot more complex, right? So given this situation, how could you go ahead and actually try to train the system? Anybody want to take one guess? There are multiple answers, but maybe you can just think about this. How would you do this, Ethan? Remember, we're doing iterative training, right? So Tobias?
I'm not very sure, but I guess what we want to do is we want to match whether our output is in the same order. So maybe we can do something similar where we find the most probable one for each kind of subsequence.
So what you can do, something along that line, I can just arbitrarily assign an initial alignment, right? Saying this is how it's aligned, either randomly or based on some heuristic or any other rationale. And then I just train the network using these randomly assigned initial alignments, right? But are these initial alignments going to be correct? No. So what I can do thereafter is, once I've trained the models, I can go back and re-estimate the alignments. And I would expect the re-estimated alignment to be better. And then I can use the re-estimated alignments to go back and retrain my system. Very simple idea. Now, how do I re-estimate the alignments? I've just sort of glommed it all into this one little bullet point saying using the decoding methods already discussed. And how do you use the decoding methods already discussed? So here's what we really want to do. You're given an unaligned k-length symbol sequence. The input is length n. And so what you really want to find is to find so maybe my slide is not very clear, but you have something like B, E, or something of that kind, right? I have something else. What you really want to find, you have only 4 symbols over here. You might have inputs x1 through xn, x10, so you have the input is 10 long. So from this term, you want to find something of this kind. B, 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 E, E, how many is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? You basically want to find an extension by repetition of the basic sequence such that the extension by repetition is the same length as the input. So in other words, you basically want to repeat my symbols. Over here I've generically called them S0 through Sk minus 1. You want to repeat the symbols in order where the number of repetitions of any given symbol is not known, such that this final length is the same length as my input. And you want to find this order of repetition which makes most sense according to my training data. Yes?
So does it matter if instead of having 2 R's and 3 B's, I would have 4 R's and 1 B?
It does. Okay. Yes.
It's a really dumb question, but it's probably relevant. But each phoneme in itself is a sequence. They're not uniform across the frames.
So each phoneme is, we don't know the length of each phoneme.
Yeah, but it's also like E is different as it goes along. It's not a E, 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 E. It's,
As far as we're
we're going to presume that
basically, all we are saying is, when I think of it this way, if I extend it this way, what I have done is I've said that this length of audio with an E at the end
yeah.
is the same as having many repetitions of E all the way to the end.
Yeah. Although in reality, each frame would be different.
Yeah, it doesn't mean that the underlying audio is exactly the same.
Yeah, yeah.
It's just the final
Yeah.
symbol is the same for everyone,
Yeah.
right? So the different meanings of the two, the symbol versus the input, right? But everybody understand what we are trying to look for in this case, right? So how can I do this? Now here is what I have as my initial map of probabilities. I could go back and do the usual thing. I can just find the most likely sequence of symbols. If I find the most likely sequence of symbols, this won't match what I want, right? Here what I want is, in this particular example, I want beefy, right? But the most likely sequence of symbols is something completely different. So just directly decoding my input is not going to give me what I want, right? It's in fact going to produce a whole number of symbols which are not in the list of symbols that I even want. So what can I do? Let me get rid of the symbols that I do not want. I know the only symbols I want are the B, the E, and the Phi in this case. So I will just retain those 3 rows in my output. And now over this output, I can go back and look at the most likely sequence of symbols. And so mechanically, procedurally, what would that be? The network is actually going to produce the entire table of outputs. I'm going to pull out those 3 rows, take them aside, and then I'm going to do perform my final decode on these 3 rows. Would this work? Anyone?
Works in the same order.
Yeah. So anybody else want to say that? Would this work? If I just decoded off this, okay, would that work? Why not?
Because the probabilities won't make sense, because the other one, if we are ultimately ignoring the other probability.
It's not about ignoring, because we are now given the information that this recording only contains the sound B, E, and Phi, right? In which case you really must be ignoring the other guys. We know they have not occurred. These are the probabilities we're trying to maximize. Yeah?
Professor, I don't really understand. By ignoring the other actual probability output for symbols that we know did not occur in this segment, if those probabilities were high, should we be punishing them?
So the point is, remember that anytime you raise the probability of the target symbol, the rest of them are automatically punished. This is softmax, right? So what really the problem really is going to be exactly what Tobias mentioned, that you would get a decode of this kind, and this doesn't correspond to beefy, right? It's beefy, whatever it is. It's not what you really want. So although you have restricted the specific symbols that you're considering, you're still missing some extra information, namely the order, right? So how would you impose order now on this? Want to take a shot?
I have an idea.
Yeah. Think about it, right? What I'm doing is I'm taking all of this. What I have done is pulled out rows from here and created a table up there, and I'm going to only search in the upper table, right? Can I modify this simple procedure to impose order? Okay, I'll give you the answer, right? It's very easy. I'm going to pull out the rows and I'm going to arrange them in the order in which I want the symbols to be produced. So observe that here I wanted the output to be beefy. So E occurs twice in beefy. The first row is B, the second is E, the third is F, the fourth is E. And if I think of it this way, and if I think of some mechanism for finding a sequence of symbols through this table, where I impose the constraint that the sequence must begin at the top left and finish at the bottom right, and must sequentially progress through this graph, top left to bottom right, I'm guaranteed a sequence that will collapse to beefy. Right? Christine, make sense? No? Okay.
I don't understand why this would guarantee that it would be beefy.
Okay, think about this. So what are the constraints I would need to put in order for this to be to guarantee that it's going to be beefy? So what I really need to do is to build a graph of this kind, which ensures that when I go from the top left, so actually let me do this on the board over here, repeat this, right? So we'll use this figure a few times, and obviously I'm not going to get to the end of this lecture today, so we're going to have to take up a couple more lectures on this topic, but it's good stuff. So let's say here is my table, right? This is, these are, so this is B, this is E, this is F, this is E. And this is time is 1, 2, 3, 4, 5, 6. Correct? So these are all the probabilities that I pulled out and set in a table. And now I'm going to impose the simple rule that if in any row I have picked, I'm going to say that in this first column I'm only allowed to choose this first guy. Okay? So that means my first column is going to be, my first time instant is going to be aligned to bar. I'm not going to allow to choose any other guy. Okay? Now at every subsequent column, I have this simple constraint that the one I'm allowed to choose, one I'm allowed to choose must be one greater or equal to what I had earlier. So over here, I'm allowed to either choose this one or this one, but I'm not allowed to choose any other. Right? If I have chosen this one, I'm allowed to either choose this one or this one, but I'm not allowed to choose any other. If I've chosen this one, I'm allowed to choose this one or this one. And that actually composes an entire graph, right? I'm going to have this graph, and this would not be required. You'd have this graph, and so what you would have is every path if I choose any particular path through this graph, in fact, even this is not going to be required. If I take any path from the top left to the bottom right, Christine, does that make sense? Right? It's going to visit every symbol. It's going to visit the symbols in the sequence that I desire because of this constraint. And now I'm guaranteed that the alignment I get is actually going to collapse to the word sequence that I choose, because this is the input length. This is the symbol sequence length. Any path can be collapsed to a sequence of symbols on the y-axis, right? Tobias, you look.
Yeah,
So for every sentence that you're supposed to decode, you're going to generate this table and then search through all
Yeah.
the possible.
Yeah, exactly, right?
Won't that take forever for
No, it won't. So that's the whole point, right? So the way we're going to, and the reason for this first, how do I decide how to find a path? What is the probability, what is the score assigned to any path? I'm trying to find the most probable sequence. Remember, the network is assigning probabilities to every symbol. So when I have a sequence of symbols, like this one over here, the sequence of symbols has a probability assigned to it. It's going to be the probability of this symbol here, times the probability of this symbol here, times the probability of this symbol here, times, basically it's the product of the probabilities of all the symbols on the path, right? And what we are really asking is, find me the most probable sequence subject to my constraints. If I didn't subject it to my constraints, I will get some rubbish. The specific constraints that I'm subjecting it to is that anytime I have a B, the next symbol can either be a B or an E. Anytime I have an E for the first time, the next symbol can either be an E or a F. Anytime I have an F, the next symbol can either be the F again or a final E. And the two final requirements, the first symbol must be a B, the last symbol must be an E, right? The second E. So if I subject this constraints and then I ask to find the best sequence within this constraints, basically what I'm doing is I'm trying to find the most probable symbol sequence path through this graph.
So you only ever have a pairwise.
It could be more generic, right? But the point is, we've composed a graph which represents all of our constraints, and we are finding the best path through this graph. And finding the best path through the graph, everybody knows how to do it, right? How many of you don't? Okay, you're a professor, right? So we don't know. We're not supposed to know this stuff. That's what kids do. But it's a very easy algorithm. It's this famous Viterbi algorithm, right? And it's based on a very simple concept. So consider the best path that ends over here. The best path that ends over here is either an extension of the best path that ended over here, or an extension of the best path that ended over here. If it were an extension of this path, so if I have the same thing, if I were to draw the same thing on the board, at this point, let's consider the best path that ends over here, right? The best path that ends over here is either an extension, do I have a third pen? Yeah. Of the best path that ended here. So it's either this guy, let's say the best path that came here was this one. And let's say the best path that came here was this one. Can you see the red? Right? Something of this kind. So the best path to this one is either going to be this, or it's going to be this. I have to choose one of the two. If I know the probability of the best path that ends over here, then I just need to multiply the probability of the best path over here with the probability of this symbol to get the probability of this path, right? And if I know the probability of the best path that ended here, I need to multiply that probability by the probability of this symbol to get the probability of this path. So I have two possibilities. One of those I'm guaranteed is the best overall path. I just pick the one which has the larger probability. It's a very simple algorithm. Make sense to everyone? Yeah?
I'm still confused. Like, how do you get to know that the sequence ends that one?
Okay, so for now, let's just assume that I know the best path to this point. Assume that I know the best path to this point. If I know those two guys, then I can compose the best path to the next point. You agree on that?
Yeah.
Okay, now let's see how we can actually get all the intermediate best paths. That's exactly the question we're going to answer. Okay? Questions, anybody? No?
I have a question about why do we need to align for this? Because we don't have the alignment data information during the training, right? Because we only have the orders.
Yeah.
So why do we need to generate such a pair?
Because if you don't, how are you going to compute your divergence?
But all the paths we generate will all satisfy the order, right?
All the paths you generate over here
Yes.
will satisfy the order. Do you believe all of them?
Oh, okay. So you use the possibility of paths to
Pick the best fit.
So we're going to optimize the best path.
the
The current model, which the current model could give.
You're using the current model to come up with your best guess for the actual alignment.
Right.
And then you're going to use that to update your model.
Right, and we train this iteratively.
And you trade this iteratively, and you hope that the whole thing will kind of converge to the right answer. Right? It's a little bit of hope and belief algorithm out here, but make sense to you?
Yeah.
Right, okay. So to answer your question, so here's how you'd begin, right? I'm going to use some notation over here. Observe that symbols can repeat. I have 4 rows over here. Each row has a symbol associated with it. So I'm going to say S of R is the symbol associated with R. Okay? Now observe that also that this score over here is the same as this score for E over here is the same as this score for E over here, because the network itself is only going to produce one probability for E. I've just copied it into 2 places, right? So in other words, in this case, you're going to get I'm using the 0 through 3. So S1 equals S3, both of them are E. And correspondingly, you'd expect the probabilities in the third row to be the same as the probabilities, the second row to be the same as the probabilities in the fourth row. Make sense?
But that's just apply when they are in the same column, right?
Yeah, within each column, right? So basically, if you think of the whole thing as a row, the second row and the fourth row are identical. All right? And just the notation over here, just to be clear. And so now let's see how the whole algorithm would actually work. I'm going to maintain 2 variables. One is a best parent variable. The best parent for this guy, so B0I is the best parent for for any of these 4 rows, and none of them, there's no row before it, so all of them have none of them have any best parent, right? Now, what is the best path that stops right here? It's just that guy. At the top left corner, there is no path. It's just that one symbol, right? What is the score of the best path? That is going to be just the probability of the symbol itself, right? These guys are not allowed to be the first path, first symbol. So what is the score you would assign, or the probability you would assign, to the best path that begins at that point? No, it's going to be minus infinity. You're not allowing that, right? Or 0. You're basically not, you're saying that these things are improbable as the first symbol in the sequence. So they have 0 probability. But the first guy is going to have, no, really, we are going to say this is the probability assigned to the symbol. You could call it 1. It won't really make any difference as far as we are concerned. But let's say this is the probability assigned to the symbol. That is because that's what we're trying to optimize. Okay. Now, let's get to the next time instant. What is the best path to this one? There's only one way of getting to this one, right? So the best parent over here is simply going to be 0 for the top one, for this one. The only way to get to it is from this one, right? So the best parent is just 0. And the probability of the best path from here, which includes both these guys, is the probability of the first symbol times the probability of the second symbol. Did I lose you?
Yes, why is that 0?
That's the index is 0, that's it. Right? The probability, I'm not speaking of the probability, I'm speaking of the index, right?
Okay.
So these are index 0 through 4.
Okay.
Right? So this one, the best index in the previous row is just 0. Right? And the probability is just the probability of both symbols on that path. Right? What about this guy? What is the best parent for this fellow? It's also 0. Right? And what is the probability of this path? It's going to be this term times this term. You just multiply the two, right? So you can compute this term also. Now, when I go to the next, and what about these two guys? They're not possible. Okay, now, when I compute the second term, I'm actually not just using some heuristic, I'm using the little arithmetic over here, right? To compute the probability of, compute the best parent for this chap, there are two possible parents. I'm picking the parent with the highest probability, which happens to be the first one. Right? So the logic we are using is the best parent is L minus 1, which is the previous row, if the score for the previous row at the previous time minus time is greater than the score for the current row at the previous time. Otherwise, it's just L. Right? So the simple logic we are using here is the best parent to this guy is this one if this one's score is greater than this. Otherwise, the best parent is this one. Very simple logic, right? And the best score is simply the score of the best parent multiplied by the current probability. Very simple logic, right? And then you can do that. So you can do so. You'd find that for the ones below, the best parent has basically minus 0 as probability, so they get blocked out automatically. And then you can go to the next row and use the same logic, and each time you're going to be comparing, you'd be using the same little logic over here. And you'd compute the best parent and the best score for each node. And the score that you have for each node really now is the probability of the best path that arrives at the node, because you're building this up incrementally. Make sense to you? Right? And now I can do this going all the way left to right. And I would fill up this entire table where at each node I have the identity of the best parent and the score of the best path that arrives at that node. Eventually, I know that the final symbol must be at this node. So the score at this node is going to give me the score for the best path. But then I can trace my way back. I can find this one's best parent, that one's best parent, that one's best parent, and those best parents must lead all the way back to the beginning. And that's going to give me the entire path from beginning to end, which gives me an alignment of the input to the symbols, yes.
Why does B have a probability the whole way across? Surely 3 from the end, it should die.
Well, this is that's just the output of the network. You'd expect it to become 0.
Yeah. No, I mean, because you're constraining it to have these 4 symbols in the final output. You need at least 3 frames to account for the others.
Yes, so, but the point is that gets accounted for by the fact that I'm actually not considering these 3 at the end.
Oh yeah, but you can't go from B through phi E in one step.
That's right. So, but computationally, yes, I'm just going, if I ignore those, everything will automatically just fall out of it, right? So, procedurally speaking, the right thing will happen, yes.
So can I go back to the previous slide?
This one?
Yeah. So here you were saying that we know the best pattern for the next column based on the
previous column
for the previous one. And let's say that I know that in the second column, the first one has a higher possibility compared with the second one. Then why we still considering the third in the third column?
So okay, so over here you're saying that if I know that this has the best parent, why am I also considering this one?
So for example, the third column, we know that the first one comes from the first one, right?
Okay, right.
This one comes from, and in the second column, we know that the first one has higher possibility compared with the second one. So so this one, let's say it has possibility of 0.6, and the second one has possibility of 0.4. So we know that the first one is the best pattern here.
Okay, till here, yeah.
Yeah, so we only compute the next two coming from this one?
So the point is, in that case, you're ignoring what can happen out here.
Yeah.
Right. So basically, the point is, when you work your way all the way to the end, if you just stay greedy, you're going to get lost very more often than not. Just think about your own logic, right? If the first guy, just magically, because my current network is poorly trained, if the first row is always the most likely, then if I keep ignoring everything that the first guy doesn't, the current best path doesn't lead to, right? I'll end up at this box at the end, which is wrong. Just using your own logic. Does that make sense?
I'm not saying that the first guy is always.
I know, if it were, I'm just saying in the worst case, right? If across the row, the first row were always the most likely. Correct? Then what I would find is that the most likely sequence is just going to be this one term. Because you'd be ignoring the rest of them using your logic.
Okay.
Correct?
So we are doing this to avoid that situation.
You're making sure that you actually get something that goes through all four symbols. So you do need that.
Okay.
Make sense?
Makes sense.
Yeah.
So on column 1 to column 2, you don't have a transition from E to E.
Which one? From?
From bird to bird, E to.
I don't have a transition.
From
This E to.
horizontal one.
Oh, no, this is because I've already, I'm assuming that I found the best path. And I'm just storing the best paths.
Okay, but it would be there in the original.
Yeah. So the blue ones are just the best paths. This is just my illustration, right? So you get the idea, right? And then what would happen now is that once you're done with this whole algorithm, this is just a little algorithm for just tracing your way backwards. You just find your way. You take the last node in this grid, and then just keep walking your way back through the best parents till the first one. You get the symbol sequence, and maybe you get something of this kind, right? So what's the next thing you do? You're going to assume that the sequence that you found is the target sequence that I'm going to train my network with, right? Remember, when I had a full target sequence, I knew exactly how to train my network, except that nobody gave us a target sequence. They just gave us this compressed symbol sequence. So what we did is we started with a compressed symbol sequence. We had an initial network, and we somehow found an alignment of the compressed symbol sequence against the input. And that's going to be this guy over here. And they would use this as my target sequence, and I can go back and train my network. And training my network, it's exactly the same thing. This is just standard gradient descent, except now the gradients are with respect to the symbols on the best path, the most likely path, rather than anything that is given to you. Right? And I can repeat this process. So I would have some initial alignments. Then I can train a model with the given alignments. I can decode to obtain better alignments, go back and train my model. But then implementationally speaking, there are a couple of different ways of implementing this. In the one case, I can take my entire training data and find the best alignments for everything. Then go back and use those alignments to train my model, and then repeat the process. Or in the other case, even as I'm performing stochastic gradient descent, I can locally just find the alignment and update the models as soon as I find the alignment, which means that one pass through the data is going to give me many, many updates of my model. Because after seeing each instance, each training instance, I would have updated my parameters. Right? So different ways of doing it. But the basic idea remains the same. When you're not given the alignment, you will guess the alignment and then work with this guessed alignment. It's not a great procedure, really. Right? But the whole point was, it works. It will not, if you have enough data and enough patience and enough time, I assure you that it will work. But in more practical situations, it's kind of, when you're working with any finite, any limitation on your resources, you're going to find that it's heavily dependent on the initial alignment. If the initial alignment is off, if the initial alignment is crappy, you're going to end up in a poor local optima, and then you have a problem, right? So can I avoid this? So let's go back and take a look at what really happens don't look at the board yet. So think of this one, right? Let's go back and actually, I'm not actually going to draw the grid, I'm just going to draw the graph, just for convenience sake, okay? So what we had was a graph of this kind. I'm assuming you can see my symbols. We had, these were the rows in my table, and from the rows in my table I composed a graph. Hopefully I can, something amazing has happened to this pen. It's writing red, black, and blue. So, do you see that? And it's actually got this gradation of black to red. Okay, so but this was the graph we computed, right? This was, so this was our graph. So this, well, we don't need this. This was all we had, right? This was the entire graph that could actually align the input to the output. Now this graph, how many paths can you find through this graph? A large number. Technically it's going to be whatever, some exponential number of paths through this graph, right? You can think of, so every one, this path actually represents a probability distribution over paths. Think about it. This one graph represents many paths, and each path has a probability, right? So you can think of this path, so I can just maybe lay these out horizontally, like so, where each point over here represents one path, maybe something like that. That's this guy, right? Maybe this guy is this guy. So let me represent symbolically every path through the graph as one point on my graph. Okay? So then for each path you're going to have a probability. Some probability, whatever the probability may be. Right? And what did we actually do when we chose our alignment? We chose the most likely path, right? We chose the most likely path, the one with the highest probability. But then choosing just one value is always a very noisy estimate. What would be a better way of doing it? Use every single path along with the probability of the path itself. Right? So in other words, instead of simply maximizing the summation of the log probabilities of the symbols on the best path, what you can do is to define the divergence. You can assume that there's a probability distribution of alignments. Selecting a single alignment is the same as drawing a single sample from it. What we've done is always draw the most likely sample. But a better thing to do is to just sample the whole thing many times, right? Draw every sample, and if you keep repeatedly sampling things, the more likely things are going to come out more frequently, the less likely things are going to come out less frequently. So if you average over all of them, you're really computing the expected divergence over all possible paths. Right? And this makes, statistically speaking, this makes more sense. Everybody get that? Right? And the expectation is a linear operator. I can just move the expectation inside the summation. Again, this guy is the negative of the sum. This is the log probability of a single path. But what you're doing is you're summing over all of the time steps, and you're summing, and the term you're summing is the log of the probability of the symbol at that time step. So, and you're taking the expectation over this entire set. I can move the expectation inside the summation, right? And so what you'd be doing, now the divergence is going to be the sum over all time of the expectation of the log of the probability of the symbols at that time, right? This, when I speak of an expectation, I'm not speaking anymore of a single symbol, right? what am I really doing? I'm saying I want to sum over all possible symbols, the log of the probability of that symbol, weighted by the actual probability of the symbol. But what is this probability? It's conditioned on everything that you know, which is the input audio and the input sequence of the compressed symbol sequence that you were given. So in other words, you're basically saying, I know that these guys are x1 through x6. I know that this is s1, s2, s1, s4, whatever it might be, right? And given this vertical axis, the identity of the vertical axis and the identity of the horizontal axis, what is the probability that of this guy? What is the probability that a randomly drawn path will go through this node at this time?
Summing all the possible paths leading to this.
So basically, yeah, but no, that's not just everything leading in, but also everything going out, right? But this term over here is the conditional probability of a path going through a particular node at a particular time, given everything else. You would do this, you'd compute it for every one of the nodes at each time, and that probability is going to multiply the log probability assigned to it by the neural network at that time. You're summing over all symbols, and then you're summing across all time, and that gives you this expectation. Anybody confused with that? Yeah.
I'm just wondering, does this still mean, like, this doesn't relax the constraint that we have to draw the graph? We still have to draw the graph?
Everything's over the graph because you're still saying it's given. Those are the givens, right? I have not relaxed any constraint. All I've said is that instead of choosing one path through this graph, I'm going to take the expectation over all paths.
So that's going to be the expectation that there's a path go through that node at that time, right?
That's the probability. So the expectation over all paths. I'll answer that, isn't it?
Because you have blackout spaces, then the summation of the probability is not 1, right?
It's the conditional probability, right? Observe this.
So it's not exactly divergence, but because you are missing a little bit.
What are you? No. This is conditioned on everything. So when I black out these portions, the part of the conditioning is that this is not possible. This is also part of the conditioning, right? The condition is that you want this symbol, you want this, and this has been observed. Those are the two conditions being given. If those are the two conditions being given, that condition means that this portion cannot happen, right? This is really part of the condition. Yeah? Yes.
With your first approach, you knew exactly where you're outputting a given sequence at a given time. Now, because you're adding up all the probabilities, you don't know that at a given timestamp, this is the phoneme that I'm supposed to.
No, you don't know. So you're assuming you're going over all possibilities because you don't know for a certainty. That is exactly what you're taking advantage of, really.
So because like we are adding up all the things, aren't we just like multiplying by 2 all of those entries?
No, we're not. So where? So basically look at what's happening over here. This figure is destroyed. Let me redraw it with my black and red pen. So we have actually, let me draw a smaller figure because we're going to run out of time pretty quickly. So let's say I have something of this kind and I have just 3 rows, right? So you're going to have this. This is my graph. This is my graph, right? Everything has to start here and everything must end over here. What we are really saying is, instead of choosing one path, we are taking the likelihood expectation over all paths, but that really means that I can take I can sum over the individual times, and at each time I'm saying what is the probability that an arbitrarily chosen path is going to go through this node. That is the p term over there. That's conditioned on the graph, right? And that is multiplying the log probability assigned to it by the network. And then I'm going to say, what is the probability that an arbitrary path goes through this node? And then I do the same thing. Then what is the probability that an arbitrary path goes through this node? And then I do the same thing. And then I add them up and I add them up across all of the columns. Right? Sang, make sense?
Yeah. I have a stupid question.
No such thing as a stupid question.
So with the first column, do you take y0 as 1, or do you take its original probability?
So ideally, it's going to be 1, right? This probability is 1.
And normalize the...
So, but so the point is, we will get to that arithmetic. We'll see where that arithmetic comes in. We're going to use the forward-backward algorithm, right? But for the first column, that would be 1. You're right. Yeah.
I was thinking about if that has a relationship to entropy, because it looks like entropy term.
Which one?
P log y.
It looks like entropy. You're really looking at the cross entropy between the posterior probabilities assigned to the nodes and the probabilities assigned by the graph, and the probabilities assigned to it by the network. You're absolutely right. Right? But the problem really is, how do you compute these posterior probabilities? That ends up becoming a problem. Okay. Yes.
Could you just once more explain both terms? The first one is the probability that a path goes through the current term, right?
So this one is the probability of an individual path.
The one above.
Yeah. So.
I'm talking about the last two terms of the final.
So this one,
yeah.
this term. So this guy over here is basically the posterior probability that an arbitrarily drawn path from this distribution is going to go through this node at this time.
And the second one?
The second term is the probability assigned to this symbol by the neural network at that time, the log of that term.
So if you get a very strong signal that it's and you've kind of got ambiguous stuff coming up, that's what pushes it into taking that path behind it.
Yeah.
Okay.
Right. That's basically what would happen in theory. In practice, who knows, right? So everybody gets what we're talking about, right? From here on, it gets messy. Yeah. Yes, this was the easy bit, right? So then it gets messy. So this, what is this first term? This is the probability of seeing the specific symbol S at time t, given that the symbol sequence is an expansion of these guy and the input sequence, right? This is the term we need to be able to compute. How do you compute this? So this term, this guy, I'm going to be seeing basically this probability term that I'm showing. That is going to be proportional to the total probability of all paths that go through that node. Right? The probability that a randomly chosen path is going to have this node at this time. Why am I saying proportional? Because if you look at the total probability of all paths through that graph, it's not going to be 1. You're going to have to normalize to make it 1. That was your point, was it not? Yeah. So it's proportional. So what is the total probability of all paths through this graph? That is going to be the joint probability of the symbol sequence and the being in this symbol at this time. The only given that the neural network itself considers is the input. Given the input, right? So, what? Okay. If I see puzzle faces, it makes me pause, because it gets, like I said, each slide is only slightly less complex than the next slide, right? So you better get it. Okay.
Are we saying that in this case, each possible transition is equally possible?
Yeah, we're assuming that all transitions are equally possible, right? All of them are given a probability of 1 in this particular case. Right? So it's probabilistically speaking, it's a mess, but because they should ideally be summing to 1, but we are ignoring that for now. Okay? And this we're going to compute using the forward-backward algorithm. So what is the forward-backward algorithm? Look at this guy again. So mathematically, I can say the joint probability of, so what the total probability of this graph is going to give you is the joint probability of the compressed symbol sequence and the probability of being in this particular E at time 3, given the input, right? So I'm just writing this explicitly as the probability of the symbol sequence and being in that particular, observing that particular symbol at that particular time, given the input, which is the same as saying, and this is where it gets messy, this is the probability of this compressed symbol sequence and the probability of seeing this symbol at time t and its successors at time t plus 1, right? Because if you're seeing this symbol at time t, it naturally means that its successors are being seen at time t plus 1. One of its successors is being seen at time t plus 1. Nothing else is possible at time t plus 1, right? That is going to be, so when I say successor, it's basically, this means that the symbol at time t plus 1 belongs to this set of successors, right? Everything else builds off this. Now I can decompose the graph into two parts, which is the portion of the graph that actually leads into this node and the portion of the graph that goes out from its successors. Yeah? And so something interesting happens, which I'll stop after pointing this out. What you would really do is, if you wanted to compute the total probability of the entire graph that goes through this node, I can write this as the product of the total probability of this portion of the graph times the probability of this portion of the graph conditioned on this graph. That's just Bayes' rule, right? Because the complete graph includes the red and the blue portions. So the probability is going to be the probability of the blue portion times the probability of the red portion given the blue portion. That is correct, perfectly correct, right? And now, in the case of a neural network, we're making a very interesting assumption. These are the probabilities of output symbols, right? So long as I know the initial symbols over here, I can ignore everything else that happened in the past. So what this means is that I can first, Bayes' rule, I can compute this total probability as the probability of the blue graph, which is the probability of all symbol sequence going up to this symbol, of the compressed symbol sequence going up to this symbol, and being in this symbol at time t, times the probability of the red graph, which is the probability of the rest of the symbol sequence, which may or may not include E, given this graph, which is entirely represented by the fact that the symbol at time t was this guy, right? So this is still mathematically perfectly correct. We haven't made any assumptions. And then we're going to do something. You see, if you're watching really closely, I have two red arrows over here showing dependencies, right? I change them to gray. So we are saying that this can be restated as the independent probabilities of these two subgraphs, right? Which means we've got rid of the conditionality. Why could we get rid of the conditionality? We are saying that the fact that it's conditioned on the input x captures everything that you need, and that you don't need additional conditioning through the graph. Does that make sense to you? Right? The assumption we are making, right? And the reason we can make this assumption is this very simple thing. It's that the outputs assigned, the probabilities assigned to different symbols by a neural network are conditionally independent, or at least you can be assumed to be conditionally independent. Look at what a neural network does at any time. It takes the entire input. This is deterministic. X is given. From the input, it actually computes a very deterministic set of hidden values. And the hidden values decide what the probabilities it assigns to the various symbols are, right? So if I give you this guy, these things are conditionally independent, graphically speaking, right? But this H is completely determined by X. So if X is given, these terms are conditionally independent, right? Which means that the probabilities of these symbols do not depend on this probability. Since the probabilities of these symbols don't depend on this probability, I can write the whole thing as the product of the independent probabilities of the blue and the red graphs. Right? I'll stop over here and pick up from here in the next class. Any questions? No. So this is tough stuff, okay? And for the next two classes, it's going to get just a little more puzzling and head scratchy. So be aware.